All right, so we are into section 1.5 of Math 146. This one is going to focus on solving exponential and logarithmic equations. Um, as I've said in prior sections, I definitely have to assume that you understand some of the basics here. I'll try and go through some of the stuff very quickly, but definitely the examples here are going to be important. It is really important, I think, that you actually understand exponentials and specifically log or logarithmic expressions and how they work and what they mean. Um, Not something I have in a whole bunch of time to go over. So again, I have to assume that you kind of understand some of this stuff. So this might be a 2 video lesson where we do some exponential and logarithmic equations to begin with, and then the second video would be some application-based stuff with exponential growth and decay type stuff. All of this is essential for being able to be successful in calculus in the next levels. Okay, so let's get started. Solving exponential equations. Let's start off with exponential functions to begin with. The general idea behind an exponential function is that the base is a constant while the exponent is the variable. So an exponential function would look something like a to the x power. There are very specific properties here for this. A, the base, must be greater than 0 and cannot, let's just say it this way, yeah, A cannot be 1. And if you think about why A can't be 1, if you have 1 raised to a power, 1 times itself any number of times would give you 1. So it would not take on an exponential property at all. The general idea, excuse me, the general graph behind an exponential function, and this is just your standard exponential function, would look something like this. So basically, after after the values of x become positive, the graph begins to grow very, very quickly. And with negative values, the values tend to make your function smaller and will actually approach 0 for a value, for a y value. Very important that you have a general understanding of the graph. Now, obviously, the graph can move, it can be shifted, it can be rotated, flipped, all that kind of stuff, depending on what's happening. We'll get into some of that stuff at some other point in time. All right, so an exponential function, and if I didn't mention it already, we will actually use the calculator a little bit here. I want to make sure you have an understanding of where to find some of this stuff and how to do some of these things in the calculator as well. So let's start off again with so basic idea. um, because we're going to be dealing so much with exponentials, laws of exponents are going to be very important. You have to remember that if you multiply common bases, something like x squared and x to the third, you would add the exponents together. So something like, and this is not an exponential equation, but x squared times x to the third would give you x to the 2 plus 3, which is x to the fifth. If you divide common bases, x to the fifth divided by x cubed, you would subtract the exponents and be left with x squared. And then if you raise a power to a power, for example, x cubed, that's a cube, raised to the second power, really what that means is x cubed times x cubed. And then you've got common bases, which then you would add the exponents together and you would get x to the sixth, or another way to think of it is when you raise a power to the power, you multiply the powers. All right, that was a very, very brief uh, kind of going back into properties of exponents. There are other properties of exponents that you probably should know. You should know that any number raised to the 0 power is 1. Any number raised to a negative exponent reciprocates it, or basically makes it the reciprocal. I'm not writing that down. Um, and then again, 1 raised to any real number is going to always be 1 because you're multiplying 1 times itself any number of times. All right, let's do some examples on how to actually solve some exponential equations. um, One of the more common bases for an exponential equation is e, which is actually a number, and it is kind of an important thing that e, which represents a number, is approximately 2.71. It is very much a number like pi, where it's an irrational number. The decimal does not ever repeat, and there's no discernible pattern, so it's considered an irrational number. It's actually defined by a specific limit formula, which is not something I'm going to get into. It is in the book. It's very interesting, actually. It just takes a little bit of time to develop. Um, but yeah, if you want to and you want to take the time, I would strongly suggest taking a look at where E actually comes from. It was actually, most people think it was developed by Leonhard Euler. Euler spelled E-U-L-E-R. So I think that the letter E kind of stands for his last name. It's probably where it came from. I'm guessing. It's not really a fact. I'm just not sure. All right. So let's go ahead and solve some equations. So let's say that we have our first example. Let's say that we want to solve the equation 3 to the x plus 1 power equals 81. So you're asking yourself, what value of x would I plug in to make 3 to that power equal 81? This is probably something you could figure out intuitively as long as you kind of know your powers of 3. But the general idea here is, can we rewrite both sides of the equation as the same base? And you can actually. 81 just happens to be 3 to the 4th power. Again, I don't necessarily know that everybody's just going to know that one off the top of their head, but that's what it is. It is 3 to the 4th. And now what you have is you have an equation where both sides of the equal sign have exactly the same base. So if I'm taking 3 and raising it to a power, and that has to equal 3 raised to a power, well, if that's the case, then the two powers must be the same. So ultimately, and we are not canceling anything out, so please don't think that's what is happening. We are just setting the powers equal to each other to solve this. So we know that x plus 1 would have to equal 4 in order for this to be a true statement. Subtract 1 on both sides here, and we would get that x equals 3. Which makes sense, because if you plug 3 in for x, you would get 3 to the 4th power, which of course is 81. All right, let's try one that looks a little bit different. Let's say that we have 4 to the 2x minus 1 equals 8 to the x plus 3. Well, the problem with this is you can't make 8 a base of 4. It doesn't work. But both 4 and 8 are powers of 2. So we can rewrite them as powers or bases of 2. So we can write 4 as 2 squared. Don't forget that's being raised to the exponent 2 minus 1. 8 I can rewrite as 2 cubed. But again, that is being raised to the power of x plus 3. And then, like we just talked about, if we have a power raised to a power, which we now do, we can multiply the powers together. So we get 2 to the 4x minus 2, which is going to equal 2 to the 3x plus 9. Now what we have, once again, is the bases on both sides of the equation are identical. So if I've got 2 raised to a power equals 2 raised to a power, that means the powers must be equal to each other. So 4x minus 2 has to be equivalent to 3x plus 9. We subtract 3x on both sides and add 2 to both sides, we would get that x equals 11. And that would satisfy your equation. That'd be something you could certainly plug into your calculator to double check when you plug that in, because those are going to be some big numbers there. that would be 4 to the 21st power would equal 8 to the 14th power. I'm not even sure if the calculators can handle numbers that big. Probably can, but in any case, that would be the answer there. All right, let's try another one. So both of those two things had things that we could make common bases out of. Let's try e to the negative x squared equals e to the x, that whole thing squared, times 1 over e cubed. Now just remember, e is a common it's a common base. It's a constant. It's just a base. It's greater than 0 and it's not equal to 1. So this is acceptable. So the first thing we can do is we can rewrite using powers of exponents the right side. The left side is pretty much fine the way it is for now. So we'll have e to the negative x squared. So let's go ahead and distribute the 2, the power of the 2, to the e to the x. So we should get e to the 2x times 1 over e cubed. There's two different ways we could do the next part. We can either write e to the 2x times 1 over e cubed as e to the 2x over e cubed, or we could rewrite 1 over e cubed using negative exponents as e to the negative 3 power. Either way works just fine. So I am going to choose to rewrite e to the negative 1 over e cubed as e to the negative 3. So we'll have e to the 2x. Now it'll be times e to the negative 3. And what we have now on the right-hand side are common bases. When you multiply the common bases, you add the exponents. So we end up with e to the negative x squared equals e to the 2x minus 3. And now the bases on both sides of the equation are the same, so we can set the exponents equal to each other, which then leaves us with a quadratic, which we can then solve by moving everything to one side or the other, getting it one side equal to 0. So let's add the x squared to both sides. And then we can go ahead and factor if factorable. If not, quadratic formula would work here, but this one is factorable. Those both have to be x in the beginning, 1 and 3. And since the 2 in the middle is positive, the 3 has to be positive and the 1 is negative. So we get values of x equals 1 or x equals negative 3. And in this case, you are going to want to double check just to make sure that those actually do indeed give you the actual exponents. If you plug in 1 and negative 3, it does actually work. So that is your solution set in this case. All right. I think we'll go ahead and move on now to some logarithmic examples. One of the biggest things that you have to remember about logs, or maybe you hopefully you were taught this, but logs are just exponents. They take on all the same properties of exponents. They're just written in a different way. And that's because logs and exponential functions are inverses of each other. And we'll kind of show how that works as well when we go into solving some of this stuff, I believe. So let's go ahead and set up for logs. Give you some background on log functions. All right, so a log function looks like this. So if it was y equals, it would be something like log, instead of writing the whole word logarithm, of x, where x is considered the argument, base a. So the x is the argument. It's what you're taking the log of. The a is the base, and then y is what the log is equivalent to. This is equivalent to the exponential equation, x equals a to the y. Now, remember when I said that logs are nothing more than exponents? If you look at these equations, you can see that the exponent of the exponential equation over here is y. That represents an exponent. That's pretty clear. But by definition, y is that log. So, since y is that log and y represents the exponent of the exponential equation, a log is an exponent. It's just written in a different fashion. It's written in a different way. It's defined in a different different way. Just like with exponentials, the base of a log is the same thing domain-wise as the base of an exponential. This a value right here is the base of the log, just like it is the base of the exponential. It must be greater than 0 and cannot be 1. Okay, those things are the same. The domain of a log function, in other words, what you can take the log of, a log domain x here, or your argument, must be greater than 0. You cannot take the log of 0, and you cannot take the log of a negative number. And the main reason for that is, if you kind of transfer this into the exponential idea, if I take a from the exponential, which is right here, that is a positive base. If I raise a positive number, to any kind of an exponent, I am basically saying, if you know the ideas behind exponents, you're multiplying the base times itself that number of times. I'm going to take a positive number and multiply it times itself any number of times. There is no way to get a negative number by multiplying two positives together. There is also no way to get 0 by multiplying two positive numbers together. So that's why your domain of the log functions, you cannot take the log of 0 or a negative number, because when you change it into an exponential, it just doesn't work. So let me kind of put up the graph of a log function. This kind of helps with the domain idea. Your log function looks like this. And that left part of the log function, where it goes down, approaches the y-axis, but it never gets to it. So basically, that's what I was telling you. The x values cannot be 0, they cannot be negative. Now, obviously, that changes if we shift everything left or right, but any standard log function, that's what happens. And then as the x values get bigger and bigger, or more, go off more to the right, the log function still increases, but it does not increase very quickly. It goes very slowly, actually. It's one of the slower growing functions. So let's go ahead now and use these ideas to solve some logarithmic equations. And since we're starting kind of a new part, we'll go back to an example 1. Okay. So let's start off with, no, let's not do that example. Let's do this one. Let's do 2 log base 5 of x, that's a 5, equals log base 5 of 9. Principles are pretty much the same here as to what we were doing with exponentials. If we have 2 logs with exactly the same base equal to each other on either side, that means their arguments must be the same. There is one small difference here, the fact that we have that 2 as a coefficient. So this is where properties of exponents still come into play. You're kind of going to take these in reverse. You're going to go backwards. Right now, what I have over here is a 2 times the log. But remember, a log is an exponent. So when you multiply an exponent by an exponent, it's because what you really had was the exponent raised to another exponent. That might all be confusing. A lot of people just kind of remember the property, and that's fine if you need to for now, but that is the reason why you're actually going to do what we're getting ready to do. You can take the coefficient, that 2, and you can bring it up to be the exponent of the argument. So we can rewrite this as the log base 5 of x squared equals the log base 5 of 9. And the reason we do that now is because we have the log base 5 of something on the left, the log base 5 of something on the right. So those two arguments must be equal to each other. So we will simply set x squared equal to 9, which means that if we were to take the square root on both sides, we would get that x equals the plus or minus 3. Now you do have to remember your domain, so we do have to double check our answers. If you plug 3 in there, I'm going to have the log base 5 of 3 on the left-hand side. There's no problems with that. If you plug a negative 3 in there, however, you would have 2 log base 5 of negative 3, and we just talked about you cannot take the log of a negative number, so that does not work, which makes the only solution positive 3. So you do have to go back and check your answers at the end of this just to make sure you actually have answers within the domain. All right, let's try another one. Let's go with log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. Okay, so in this case, we don't have logs on both sides. Yes, we could move one of the logs to the other side, but the 1 itself is not written in log form, which obviously we could do, but we're not going to worry about that. We're going to use one of our other properties of logs, which is a condensing property. So when you have two logs with the same base being added together, again, this is just like properties of exponents, what we're going to do is we're going to multiply the arguments together. So we're going to have now the log base 5. Multiplying the arguments together is going to be multiplying x plus 6 times x plus 2, which is going to give us x squared plus 8x plus 12 is equal to 1. All right, so again, you have to think of this as properties of logs kind of in reverse. What we did was we had two things with common bases. The bases are both 5, and we were adding exponents together. Remember, logs are exponents, so we are technically adding the exponents together, which means that what we had to have had was two things with common bases being multiplied together, so that's where the multiplication of those arguments comes from. It's, again, taking the process in reverse. Again, if you don't remember it that way or can't think of it that way, which is fine for now, just remember that when you add two logs with the same base together, you're going to multiply the arguments. Now what we're down to is we are down to a situation where we have a log on one side and a constant on the other side. When this is the case, what we want to do, because the x's are in the argument of the log, we want to change this into an exponential. So you kind of have to understand how the exponential pattern works. Remember that this is your base, that's your a value. Over here, that is the exponent, because that's what logs are equivalent to. They are exponents. And then this right here is your argument, or basically your y value, I guess, from the other equation. So the easiest way for most people to remember it is this kind of like loop-de-loop kind of method. They know that you take the base and you raise it to the power over here, and that gives you the argument. So that's what we'll do. We're going to say that 5 to the first power equals x squared plus 8x plus 12, which is now a quadratic. We can go ahead and solve as a quadratic. Let's subtract 5 on both sides. So we get x squared plus 8x plus 7. This one does factor. So that would be x and x. That's going to have to be a 1 and a 7. They're both positive because we need to add up to positive 8. So that means that x is going to equal -1 and x is going to equal -7. Let's go back and check to make sure that these work. If you plug in -1, plugging in -1 in for both of those x's right there, plugging it into the first one will give you a log of +5, perfectly fine. The second one will give you the log of +1, also perfectly fine. If you were to plug in -7, however, the argument in both of the original logs would become negative, not perfectly fine. So you always have to go back to your original. So x equals -7 is extraneous. X equals -1 is our solution. All right, let's do an example where we have to use the subtraction property. And we're also going to switch this up, and we're going to do an example where it's a natural log as opposed to a standard log. So we'll call this example 3, and we will have the natural log of x equaling the natural log of x plus 6 minus the natural log of x minus 4. And just to make sure everybody knows that a natural log is the same thing as a log base e of something. Obviously, you would have, I should probably write like a little of something. Those are the same. So they pretty much just shortened log base e on the right to be natural log, which is just assumed to have a base e. It's just not usually written there. You can write the base e if you would like to, but you don't have to. It's not necessary. So a natural log is a log with the base of e all the time. All right, so properties of exponents. Once again, we are going to have two logs on the right-hand side of this equation, which are being subtracted. So if in the case of subtraction, we are going to divide the arguments. So it'll be a natural log of x equals the natural log, condensing the right side, of x plus 6 divided by x minus 4. And again, that is properties of exponents, properties of logs. So now what we have is the natural log of something on the left equals the natural log of something on the right. Because it's just one natural log equaling another natural log, we can then say that the arguments must be equal to each other. So again, we are not canceling out the natural log. Don't cross them out. That's not what you're doing. You're just taking the argument and setting it equal to the argument on the other side now. All right, so probably the easiest way to do this is to multiply both sides by x minus 4, which will leave us with an x squared minus 4x equals x plus 6. Again, it's quadratic, so let's move everything to one side. So we'll have x squared. Let's see, we'll subtract x, so it's minus 5x. We'll subtract 6, and that'll be equal to 0. So let's go ahead and factor. The nice thing is all of these have factored so far. All right, so that's a minus 6. So don't get confused on this one. A lot of people think, oh, 2 and 3, that'll add up to 5. It would if they were the same sign, but we need them to be opposite signs. So it's going to have to be a 1 and a 6, where the 6 has to be a negative, the 1 has to be the positive. So x in this case will equal -1 or positive 6. Plugging in a -1, well, right away, you can see from the original equation, plugging a -1 in there is a problem, so that will not work. That's extraneous. Plugging in a positive 6 leaves you with a positive argument for all the pieces, so positive 6 is going to be our solution set. X equals -1 was extraneous. All right. Let's get into some slightly more complicated ones. We're going to have a couple more here that might take a little bit longer. Yeah, let's go ahead and do it in this video. I still think it makes more sense to do it in this video. So we'll go with example 4. All right, let's say, this one won't be that long. Let's say that we have something like 2 to the x equals 5. Well, 2 to the x equals 5. There is no way for me to rewrite 2 in any way. There is no way for you to rewrite 5 as a base of 2. So you're kind of stuck here. Um, the only thing that you can actually do is to try to rewrite this as a log, which we can do. The answer is not going to be the nicest, but we can do this. So we're just simply going to rewrite this as a log. And the base here, excuse me, is 2, because that's the base of the exponent. Those are always the same. Remember that logs are exponents, so this whole thing is going to be equivalent to x, but I have to have something that I'm taking the log of. Well, in that case, that would be the 5. So if you want to double check what we were talking about from before, you would say, okay, does this work out if we go backwards? So it would be 2 to the x is equal to 5. Yes, that works out. So what we have now is an expression for x, which is solved. It's the log of 5 base 2. That's it. Log of 5 base 2. Okay, there's nothing wrong with that. There are other ways to solve this, but that's probably the easiest way in this case to do it. You could, I'm going to show you the other way here. You could do what is called taking the log of both sides. So instead of what we did, you could take the log of both sides of the equation. Perfectly fine to do. Now what we're going to do, because we're going to use properties of logs to solve this, we're still trying to solve for the x, which is still currently in the exponent. Remember that if you had a coefficient, you could bring it up to be the exponent. Well, we can do just the opposite. We can bring that exponent out to the front. So we could say that this is the x times the natural log of 2, which equals the natural log of 5. And then to solve for x, you would divide both sides by the natural log of 2. So you'd get the natural log of 5 divided by the natural log of 2. I do realize that these two things do not look the same. However, using what is called a change of base formula, which we are not going into, I don't know if that's something that has been taught before, you would see that they are equivalent. And if you were to plug these things into your calculator, you would see that they actually give you exactly the same value, or at least the calculator spits out the same value for you. So 2 different ways of solving it. I'm not going to tell you that one of them is more correct than the other one. They will both have uses at different various times. All right, so let's go ahead and solve this one, which is probably going to utilize the second method that we did. Oh, yeah, let's use red. Why not? We are on example 5 of this part. So we're going to have 5 to the x minus 2 equals 3 to the 3x plus 2. All right, once again, there is no way for us to write either 5 or 3 in terms of other bases, so there is nothing else that we can do here other than to rewrite these using properties of logs. Because you have exponentials on both sides, you're not really going to be able to utilize the first method that I showed you. What we're going to have to do is we're going to have to take the log of both sides. So we will take the natural log of 5 to the x minus 2, which equals the natural log of 3 to the 3x plus 2. By the way, I'm using the natural logs. You could technically use a standard log. Doesn't really make any difference. Natural logs are just easier because it's a little bit shorter to write. I know it's one letter difference, but it is. It is, in the long run, it'll come out cleaner, I think. But it's not wrong to use regular logs. All right, let's use our properties. We can bring the exponent out to the front. X minus 2 times the natural log of 5 equals 3x plus 2 times the natural log of 3. Notice that because those exponents were quantities of addition and subtraction, you put them in parentheses. The reason for that is because we're still trying to solve for x. So what we need to do is we need to distribute on both sides. So what we have is x natural log of 5 minus 2 natural log of 5, just distributing the natural log of 5 throughout. And then we'll have 3x natural log of 3 plus 2 natural log of 3, distributing the natural log of 3 on both sides. Okay, so we've gotten the x's out of their parentheses, but we do have x's on both sides of the equation, so we're going to go ahead and move those so that both of the x's are on the same side. Anything that doesn't have x will move to the other side. So I'm going to go ahead and subtract the 3x ln of 3. So we have x ln of 5 minus 3x ln of 3. And I'm going to add the 2 ln of 5 to both sides. So we get 2 ln of 3 plus 2 ln of 5. And now that we have both of our x's on the left-hand side, we're going to factor the x out, which will leave a natural log of 5 minus 3 natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. And then to solve for x, we simply divide by what's in the parentheses. So we have x equals 2 natural log of 3 plus 2 natural log of 5 divided by natural log of 5 minus 3 natural log of 3. There is ways to condense all of that, but there really is no purpose for that at this point, I don't think. I don't think it's going to make anything simplified to a nice, easy number. So that is the answer for x. Again, what that is doesn't really hold a lot of meaning to a lot of people. You could plug that into a calculator. Again, we will use calculator in this section, probably during the second video. All right, so we got one more to solve for this particular one before we actually get to a calculator question. So let's do example 6. Which is 4 to the x minus 2 to the x minus 12 equals 0. All right, this one's going to play back to a couple sections ago. So the first thing you should notice is the bases are not the same. I've got this constant. Even if I move the constant, I can't make the bases the same on either side. It's a little bit more complicated than that. So here's the idea. We should recognize that 4 can be written as a base of 2. So let's rewrite 4 as 2 squared to the x minus 2 to the x minus 12 equals 0. And then if you remember your properties of exponents, when you have an exponent raised to an exponent, you multiply them. So we get 2 to the 2x minus 2 to the x minus 12 equals 0. What you should notice is that this exponent is double that exponent, and then we have a constant at the end. So what we have is something which is quadratic in form. It's not a quadratic, but it is quadratic in form. So if we let a variable, typically u, be a substitution, we're going to say, okay, let's let u equal 2 to the x power. Well, that replaces that middle term with u. Okay, the constant stays the same. And if that's the case, u squared, if I were to square u, that means you would square this right side, 2 to the x squared. Well, that just gives you 2 to the 2x. So this first term becomes u squared. Now we can solve this initially just like a quadratic using factoring. So that's going to be a u. To get the minus 1 in the middle, we're going to have a 4 and a 3, minus 4 plus 3. So u here is going to equal either negative 3 or positive 4. All right, but again, remember we did not start off in terms of u. We did, however, start off in terms of x. So what we're going to have to do is we're going to have to plug these things back in to solve for x. So we're going to have negative 3 equals 2 to the x, and 4 equals 2 to the x. Well, if you remember how exponents work, Again, I just said if you take a number like 2 and you raise it to any power, because 2 is positive, you'll never get a 0, you'll never get negative, which means this first one has no solution. So u equals -3 does not give us anything. The one on the right, however, should be relatively obvious. We probably don't need to go through this process because you know that 2 to the second power is 4, so x should be 2. But you could rewrite 4 as 2 squared, which would equal 2 to the x, which means that your exponents have to be equal to each other, or x does indeed equal 2. So 2 is the solution to example 6. All right, we have hit the 40-minute mark, so we're going to stop this video. We're going to come back with one more exponential type equation, which we are going to utilize a calculator for, and then we are going to do a bunch of application-based problems with exponential growth and decay.